there's a world of miracles inside our bodies.
See every color on Earth. Hear sounds that inspire. Feel more than just heat. Taste a world of flavor.
Nice.
Smell the miracles of nature. See, smell, hear, taste, touch. Widen your world.
There are those of us who like to venture to the unexplored, to see the beauty in the strange and unknown. Those of us who go out there with a sense of wonder. If you're one of us, and if you want to explore more of this great planet, we're ready to take you there. It's time. Turkish Airlines. Widen your world.
Good evening, everyone. We are delighted to welcome you to Eurasia Airshow 2020's Webinar 2, The Importance of Aerolasticity for Upcoming Air Platforms. My name is Atul Chandra, and I am Technology Editor at GPP Aerospace and Defense, and will be the moderator for this webinar. I am delighted to present our speaker for today, Martin Renouy. Martin is Principal Engineer at Sterling Dynamics, and his presentation today will mainly focus on aeroelastic developments within aircraft manufacturers. Martin has more than 15 years of experience on various aircraft programs, including work he has done for main manufacturers, modification programs, and research and development. His main topics of interest are aircraft aerodynamics, loads, and aeroelastics. Just a few points on today's webinar. We will not be accepting any questions, and Martin will speak for approximately 30 minutes, following which he will answer a couple of questions which I will ask him. Thank you all for joining well. We hope you're doing well and safe. And over to you, Martin.
Thank you very much, Atul. It's a bit odd addressing you guys like this. It would have been nice to be able to do this face to face, but I welcome the invitation from Eurasia to speak to you guys this evening. I do realize it's the last session of the day. Most people will probably have had a quite a long day, so I do really appreciate for those people that are still hanging in there and willing to listen to me this time of day. I promise to keep it reasonably easy to digest, and so I hope you'll find this presentation useful. Just a quick summary of this presentation. I'll start off with just a quick introduction of the company. I don't want to spend too much time on it, but just to give you a bit of background of who we are and what we do, and then I'll go into talking about the title that I've been provided with to talk about this evening. So just a few words on Sterling Dynamics, which is the company I work for. Let's see. Oh yeah. So we're not the most well-known company in the world. We're only small. We've got about 100 people based in Bristol, but we do get involved in a surprisingly large amount of aircraft programs. I think if you look at our website, it says something along the lines of that we've been involved in 70 aircraft programs. And considering that we've been founded in 1987, that's quite a feat. As I said, we're Bristol-based. But most of our customers are covered all over the world, really. And I've got a slide later on to illustrate that. are essentially an engineering consultancy specialized in things like dynamics, aircraft systems, control, and simulation. Since a couple of years now, I think we've been owned by Explio UK. We are still very much an independent part of that organization. So Explio does let us sort of get on with doing the things we're good at and the things we've got the experience with. But we have now the flexibility of being able to combine with a big organization like Explio to bring out the best of both organizations. And as I said earlier, we are a global company in the sense that our customers are all over the world, and 80% of our sales come from outside of the UK. I'll quickly skip over, or not skip over this slide, but quickly summarize sort of our three main activities that we do in Stern Dynamics. So the department I work for is the Aerospace Technical Services, where we essentially cover most of the skills required to develop and research aircraft. So we work with OEMs in supporting their programs. We also work a lot in modification programs, whether it's small modifications or very, very large. Think about the Pax freighter conversions that have been quite popular in recent years, things like that. And we support the whole design life cycle. So from starting with the requirements up to support for certification and that sort of thing. So that, in a nutshell, is our aerospace technical services. And roughly our company is split into 1/3. So the three parts are sort of an equal size, I guess, in terms of manpower and turnover. So the second there in the middle, that's our active control technologies. So these are the products that we make, which are fully active controls, motor driven and fully tunable. So the feedback is fully tunable, which means that you can basically adjust them to represent any sort of aircraft or helicopter that you like. So that gives and the products that we make are mostly focused on the simulator market. One of the biggest sales, I guess, we have is that we support the F-35 program and provide all the active side sticks into that program. So that's an excellent product that we have, and I can see a lot of development in that area, both to the top end, where sort of so from the simulator market into flight-worthy sticks, but also to the bottom end where there's a big push now to have more and more desktop kind of based simulator setups. And on the right hand side are marine solutions, quite a niche market. We provide independent or we're an independent supplier of submarine controls and autopilot and hover systems, and that's not a huge world. I guess there's not many countries in the world that have these kind of systems, and we're very much involved in many of them. And I think here the collaboration with Explio, so our mother company, will be expanding over the coming years, where their experience with surface ships and our experience in marine will combine and build a bigger and better capability. So that's really Sterling in a nutshell. Just to illustrate that we work all over the world. I think this is just an overview of some of our recent customers, I should say. So yeah, we do get around. One final slide on before I go onto topic. So a quick overview of some of the capabilities that we have. I'm not going to go into any detail on that, but because I'm talking about aeroelastics, I guess the things to highlight are the structural analysis and the aerodynamics. and the control and simulation there as well. So those are the capabilities that we have, which combined give us this great aeroelastics capability. Just a few words on myself and my background and why I'm happy to talk about this topic for you today. I've been studying dynamics for about 15 years, straight out of university for me, where I actually didn't study aeroelastics. I studied aerodynamics in Delft University. That doesn't mean that aerodynamics has been the only topic of interest for me. I do generally consider myself a generalist with a very much an interest in aeroelastics. I've done quite a few projects over the years, including a lot of aeroelastics projects, including some of the things listed there, like gust loads analysis, maneuver loads analysis, flutter analysis and certification, store ejection loads, where you can imagine that for fighter aircraft, where you drop something heavy that hangs off your wing, that's going to have quite an impact, and even down to control system development. I tallied up all the programs I've been involved in over the last 15 years, and I came to about 27 different aircraft programs, which is in just over 15 years, I think, quite an accomplishment, and it illustrates the diversity of the sort of work that we do. So now on to the topic that you dialed in for, the importance of aeroelasticity for upcoming air platforms. I've deliberately used a Herjet picture here for two reasons. I was involved in that project in the last 2 years, and was lucky enough to travel to Turkey for that. And I think it's quite a good-looking aircraft, to be honest. It's one of those things. I think the old saying goes, if it looks right, it flies right, and I think that goes definitely for this aircraft. And I hope to have more involvement in that in the near future. So to answer the question, really, what the importance is of aeroelasticity in the upcoming air platforms, I think it's worth just having a quick look at what aeroelasticity actually is and what it means, and how we treat it in aerospace. So I've got a few slides on that. So if you go onto Wikipedia, you'll find this definition. Aeroelasticity is the study of the interaction between the inertial, elastic, and aerodynamic forces occurring while an elastic body is exposed to a fluid. That's a slightly difficult interpretation. Basically, the way I see it, it's the interaction between a flexible aircraft and the flow around it, the airflow around it. And it's often depicted in the diagram you see on this slide, where you have the inertial forces, the elastic forces, and the aerodynamic forces, all three coming together in your aeroelastic solution. It's called Collar's aeroelastic triangle, after the person that came up with this way of representing it. And essentially it means that it's any study where the dynamics of the structure couple with the airflow around the structure. I think one of the things that is actually missing from this triangle is the interaction with the flight control system, which is not to be underestimated. It's not a new concept, aeroelastics, in any means. I mean, things like flutter, it was known in the early 1900s, before World War I, that aircraft could flutter, and it wasn't. They didn't have the means to really do the analysis on it like we do today, but it was definitely something they were aware of, and it was studied widely. It was studied quite a lot in the years to follow. The term, actually, the term aeroelastic, was coined in the sort of 1930s at the RAE in Farnborough, which is actually about 1 mile down the road from where I live, coincidentally. So that is sort of the depiction of the main basics of what aeroelastics is. Looking at what that actually means in terms of aircraft analysis, there's a few topics that we cover. Flutter is probably the most well-known one, especially for the sort of videos that you see on the right-hand side. So that is a very clear example where the structure and the aerodynamics are coupling, and which has quite spectacular results. But it's also Aeroelastics also covers the fields of, for example, aircraft loads, where thinking about gust and turbulence loads, where anyone that sat on an aircraft that went to turbulence and has looked at the wingtip knows how much impact that has on the behavior of the aircraft and how much it loads the aircraft. So gust and turbulence is important. Maneuver loads is important, because you can imagine if you're putting a steep turn, especially on a military aircraft, the impact that has on the structure. Store ejection is an interesting one, very specific to military aircraft and not always considered necessarily as an aeroelastic thing. But you do twist the wing quite a lot during store ejection. It can be quite a violent event. So it does require aeroelastic analysis. One other thing to pick up on there is the buffet, which is at the bottom, which is sort of a special case, and I'll get to that very shortly later because I'm quite conscious of the time that I've taken up already. So just quickly continue. So aeroelastic solutions can really be broken down into the very straightforward linear solutions, and then depending on what your requirements are, an increased level of complexity. So for most of the work that we still do, the linear models are still very much in use. It's the best way of doing it for most solutions, and one of the reasons why they're very popular is also because of the speed of linear solutions. So if you think about an aircraft loads program where you'd be running potentially tens of thousands, maybe hundreds of thousands cases, then solution run times need to be very quick. And that's where linear solutions come in. So in terms of aerodynamics, you'll be talking about the doublet lattice methods, where you basically only panel the outside surface of the aircraft. In terms of structure, you're talking about stick models. It's a very simple but very, very effective way of representing the aircraft stiffness and mass distributions. And then for flight controls, simple linear models are usually more than sufficient. Now, there's definitely a drive within industry and academia as well to go to higher fidelity modeling. So in terms of the aerodynamics, that means coupling with higher fidelity aerodynamic solutions. For example, Euler solutions or Euler couples with boundary layer solutions, or all the way up to fully unsteady Navier-Stokes solutions. Even though these solutions are increasing the fidelity, gives you better results. The cost of that in terms of run times is very, very large, especially on the aerodynamic side. And therefore it's not always desirable. And the trick there, I guess, is to use the solution that gives you the answer you're looking for. Similarly, on the structural side, as I said, for a lot of the applications, still a very similar stick model is more than good enough. But more and more do we see that people are going to these sort of GFEM kind of detail, and that's still linear, but a lot more degrees of freedom, and therefore a much slower solution. But the cost of that is actually not that great. So it's not as big a step, I guess, as going to the more complex aerodynamic solutions. And it has many benefits. It's simply the fact that you can model the aircraft in more detail. is a big benefit. If you think about military aircraft and you've got short stubby wings, then is a stick really that representative? Probably not. And it gives you the option of doing things like direct stress monitoring and having a common model with the stress department, which is a great benefit. And then if you do need to go one step up in terms of fidelity and go into the nonlinear structures, then that is a big step to take generally. And it's only unique cases where that is a real benefit. For example, where you have very, very highly flexible structures, or the picture. I'm not sure if the picture is very good visible, but this is a flapping wing concept that Airbus has been studying, and it's this sort of structures where the simple linear models will just no longer give you the solutions that you need really. Just to quickly talk about the flight control systems in this. So I think the flight control systems is very much a part of Aeroelastics, and generally fully linear or piecewise linear model is perfectly fine for most applications. But it's not a huge step to go to fully nonlinear. So that's where that step is generally worth taking. Also, because it takes away some of the unknowns you might have, or some of the less assumptions you might have, which might put some of, for example, de-risk some of your flight testing by having a higher fidelity model there. So I think for me, one of the things that makes Aeroelastics an interesting topic is the fact that it brings all these things together. And it does mean you're not just looking at aerodynamics, you're not just looking at structure, you're not just looking at flight controls, but you're looking at all three of them, and basically you need to have an understanding of all those topics. When it comes to these technology, I think one thing to point out is most of it is reasonably well established in terms of the theory behind it, but the challenge often comes from the integration. And I think that's where still a lot of development is being done. Right. So to get to a better understanding of the importance of some of this for the upcoming programs, I think it's important to have a quick look at what sort of upcoming programs there are, and I think we can sort of split it into 5 categories, or I have split it into 5 categories. So starting off there at the top is essentially the new programs within the existing, what I call the market leaders. You can think about on the commercial market. I'm obviously going to be talking about the likes of Airbus and Boeing, and who are clearly dominating those markets. And then it's sort of almost a black and white view, and I'm sure there's a lot of nuances in this, but I've sort of broken it down like this. So the second second one there is the commercial aircraft market from emerging markets. Sorry, so the commercial aircraft from emerging markets. So those are all the new programs from basically the companies that are not as established as some of the others and don't have the history behind it. Then the third one down the list there is and this is an incredibly dynamic market, I think, where a huge amount is happening, which is the market for manned military aircraft. We think there's a huge amount of newcomers in that. There's a huge amount of ambition, ranging from trainers and light attack aircraft to 5th generation. And I think that's a very, very interesting market to follow. And then the bottom two there, we got the unmanned air vehicles and the now very, very new topic, I think, the urban air vehicles. I think both of these are basically top categories where you see a huge range of sort of shapes and sizes and interesting ways of propulsion, a lot of rotorcraft, which I won't be talking about today, but and for some of them, aeroelastics is going to be a very interesting topic and very important part of their development. For example, if you look at the slender wings on the right hand side here for these type of configurations, but there will be a lot of sort of smaller kind of UAVs and where aeroelastics is of sort of secondary importance, I guess. So if we have a bit more detailed look at what sort of these upcoming platforms, what that means in terms of aeroelastics. So to start off with, if you think about the existing market leaders, so the companies, the well-established companies with lots of experience and a lot of time in the market, I guess. It's if you think about the likes of Boeing and Airbus, they've been around for several decades. They've had a lot of time to invest in research and development, and they've got a lot of people that have been around for a long time who have been involved in these developments, who understand the developments, who've worked on several aircraft programs, and so for them, in terms of aeroelastics, I could really see how they're going to be using these high fidelity methods to push the boundaries, really, to make their aircraft more efficient, make them structurally closer to the limits, and also in terms of the flight control systems they have, the low deviation systems that they'll have, they really will have the experience and the tool set to push the development. And the fact that they can do that, the fact that they can model at a higher fidelity and take less assumptions during their modeling phase, or use less assumptions during the model phase, it means that when it comes to their product and it comes to their flight testing phase, they will have essentially a more mature product. There will be less unknowns, there will be less assumptions and there's less risk on the flight testing, which in terms of development times means they can develop reasonably quickly. There are some challenges when it comes to higher fidelity modeling. One is the sort of the model VMV, where you have the validation and verification of models, which just becomes harder because you've got a much more complex system. So how do you approach that? And another thing is that it becomes more difficult to predict what your system is going to be doing. So if you think about slightly off design conditions, failure conditions, where you would, with a simpler model, would go, well, this is what's going to happen. How do you predict that on a higher fidelity model? So that there's some challenges there. If we then take it to the other side of the market, where basically the newcomers are, the emerging markets, both civil and military. I think a lot of this goes for both these markets. Then they're in the position where basically they've got two choices. They won't have the high fidelity tool sets. They won't have the experience, so when those that are involved in the planning and scoping of these large programs, because that's what they are, they need to make a choice in terms of, do we spend the time and the money to actually develop our processes and train our people and basically take the hit on the cost and see that as an investment, which it is, of course, in the future. Because I mean, aircraft programs, you're not talking about a few years. You may have 7, 8, 9, 10 years of development, but these aircraft are going to be around for 25, 30 years if you're lucky. So that's a choice that you can make. Alternatively, you could use the more sort of standard, I guess, linear off-the-shelf methods and tools, which still requires an investment in people. But at least it gives you a quick way into having a tool set and a quick way of getting started. Does that mean you're behind on the back foot in terms of not being able to compete with some of the more established programs? It may do in the short term, but I think in the long term, you will be able to catch up on that. But I think that the second bullet point there is an important one, and that's to really have a good look at the requirements for your aircraft, and where do you want to be in the market? What do you want to achieve, and only really develop the technology that you need for that. We've had requests for companies asking about active flutter suppression, for example, where you sort of think, well, why don't you start developing something that doesn't need that sort of system, where you can start simple, and once you can do the simple things, learn to walk first before you can run. That's essentially what it comes down to. And something else I want to stress really is ensuring that aeroelastics is included in the entire design cycle. What we tend to see sometimes in sort of emerge in newer companies, that, for example, on the side of Flutter, that Flutter becomes a check. It's basically, oh yeah, we've designed the whole aircraft, we've done the aerodynamics, we've done the structure. Let's check it for Flutter. I think if that's what you're doing, then you might be getting yourself in quite a lot of trouble, because this should be considered from day one, really. Because if you find that you've got a Flutter issue later on in the program, then the cost of rectifying that is going to be quite significant. So I'm a bit conscious of the time, so I'll skip ahead. So as I said earlier, there's one sort of special case which I want to give a bit more attention, and that is the case of Buffett. And that seems maybe a slightly odd topic to sort of highlight in this conversation. But I'm aware of, as I said, there's a lot of military programs all over the world at the moment, all very exciting programs. And if you look at the history of military aircraft development, fast jets I'm talking about, then there is you don't have to spend a lot of time Googling to find out what the main issues were in those programs. And Buffett is something that comes up a huge amount, and it tends to be overlooked a little bit. It tends to be considered to be more a fatigue problem, and therefore probably doesn't get the attention that it requires. So that's why I thought I just spend a couple of minutes and try to put it on the map. So just to illustrate what Buffett really is, I've got a little video, and hopefully that will come up. So Buffett really is an issue, or a topic that has become very, let me just do that. A topic that's become more and more relevant due to the introduction of the sort of leading edge extensions or strakes or whatever you want to call them, which are great in producing lots of lift up high angles of attack. But the downside they have is, if I just stop that for a second, is you get these big vortices, which help you produce lift, but they're unstable and they break up, as it's very well illustrated in this video. And this is a video, you can find it online. It's all out there. So there's no secrets here. But as I'm scrolling back, it's quite clear what's happening in terms of the impact this has downstream. And as you can see, the impact that has on that vertical tail, that's not what it was designed for. And this is an effect that will happen no matter what your aircraft configuration is. If you've got these sort of strakes and relying on vortex lift, then you're going to have to know what the impact is on the rest of the aircraft, whether it's on the vertical tails, on the horizontal tails, but also significantly on things like if you're carrying underbelly stores, or like fuel tanks, that sort of thing. It tends to sort of affect the structure behind it as well. So if you've got ventral fins on the back of your fuselage, they will be affected by the buffeting coming from the stores. So it's not just a problem that's a result of the sort of trend, I should call it, of the having twin tail configurations, where, as you can see from the F-18 here, I mean, it's clear that if you've got a twin tail, it's going to be a bigger problem, but it doesn't mean it's limited to that sort of configuration. F-16 I know had issues with it, and you can find plenty of other examples, and so it is something to really, really take seriously, especially because it's something that will show up quite quickly during flight testing. And if that's the point where you've detected this problem, and you've already built your prototypes and you're well into sort of completing your design, then that's a very expensive modification to be making. Right.
Martin, I'm afraid we're beyond our time, so can I request
Yes, I
that
realized
you
that.
finish too, please?
Well, about to summarize, so that's all right.
Great, brilliant. We're on time. Thank you so much.
Can I quickly summarize, or do you want to go straight into the questions?
Please summarize, Martin. We do have a minute or two.
All right. Okay. So, yeah. So let me quickly wrap up. So for me, there's two things really. There's processes and technology. In terms of processes, I think there's a challenge for some of the emerging OEMs to pick the right technology and pick wisely, because it is a big investment in the tools and the process, and especially the experience as well. And developing aircraft is expensive. It's difficult, and just think about aircraft programs in the last sort of decade and how many have struggled or failed. And not saying it's down to Aeroelastics in any means, but it does show how difficult this is, and that setting the requirements is a very important thing, and develop the technologies that go with those requirements. And that sort of takes us onto the right column there. So technology is great, and we tend to be pushed by the technical development. Where there's a real sort of technical, what do you call it? There's a good word for that. I can't think of it now. It doesn't matter. So we tend to be pushed by the technology rather than pushed ourselves by the requirements and what we're trying to achieve. So the point to make there is that great, all these technologies are great, and it's great going to these really, really high fidelity models and approaches, but be careful while you use it. I guess that's my warning there. And I'll leave it there, considering the time and the time of day.
Thank you, Martin. I must confess that was very, very interesting to listen to. And, the need for high fidelity modeling, the trade-offs, better results, but the costs are expensive. De-risking flight testing as well by use of nonlinear models. So I found these to be very interesting topics, and hopefully we can delve deeper. We do have time for a question or two, so I'd request you to be brief so we can get both the questions done for this evening.
Okay.
What role do you expect, Martin, the Sterling Dynamics would play in Aeroelastics development in the future, in the near future?
Yeah. Well, so this talk has really been sort of focused on the OEMs, so the aircraft manufacturers, and of course, yeah, it's a good question. Where do we fit in? I think the answer that is twofold, really, and that's based on the work that we do and the work that we've been doing for the last few decades, really. First of all, there's the support that we provide into the OEMs in terms of really throughout the design sort of life cycle, helping define requirements, helping them with their methods, providing expert advice. It's that sort of thing. Another thing that we do quite a lot of is actually working in parallel to them. So we don't take on their work and do it on their behalf, but we'll work in parallel. We'll develop our own models and methods and act as a validation of the OEM's processes. So I think that's an important thing that we'll keep doing, and which we're yeah, we've been asked to do quite a lot of. On the other hand, there's the modification market, which is for us probably even bigger than the support to the OEM. So this is where non-OEM companies, smaller companies, will often come up to us and say, all right, we've got this idea, we want to make some changes to this aircraft, bolt something on it, convert it to a freighter, things like that. And that's where we come in, and depending on how big the modification is, we'll either reverse engineer the aircraft or by any other means sort of support them in doing that work. So this could be loads or aeroelastics or both, and all the way through to certification. So I think that's where we fit in.
Great. Thank you, Martin. Certainly, I'm quite sure that countries in the Middle East and Southeast Asia, which are having a number of new programs, will certainly benefit from such services. Technologically advancements that we view in this field, Martin, that's our last question for the day. Where do you see the technologies evolving for aeroelastics?
I think, well, there's a lot of I think there's been a lot of focus on the aerodynamic side of things, and it's probably the field that I'm, considering my background, are mostly interested in as well. So the desire to couple structures with Navier-Stokes CFD solutions, I think that's especially in academia probably where a lot of focus is on. Is that going to be having a big impact on the industry? I don't think it will in the short run, just because the step is so big in terms of solution speed, and so I think it will stay limited to really using it for special conditions. And I think where we might see a more interesting development is actually on the structural side, where these very non-linear structures, very flexible. We've seen flapping wings now on Airbus sort of research aircraft, braced wings talking about. So I think I wouldn't be surprised if they're actually, in terms of changing the way we see aircraft, that will have the biggest impact.
Brilliant. Martin, thank you very much. I think it's been a fine session, and we are well in time. So thank you again for all those who are viewing this webinar. Martin Renoji is the Principal Engineer at Sterling Dynamics. And we thank you all once again for joining our second webinar for the Eurasia Airshow 2020. We wish you all a good week and a year ahead, and take care and stay safe. Thank you, Martin.
Yeah, well, thank you very much, and thanks for inviting me, and thanks to everyone who stuck around.
Pleasure to have you here. Good day all.
There's a world of miracles inside our bodies.
See every color on Earth. Hear sounds that inspire. Feel more than just heat. Taste a world of flavor.
Nice.
Smell the miracles of nature. See, smell, hear, taste, touch. Widen your world.
There are those of us who like to venture to the unexplored, to see the beauty in the strange and unknown. Those of us who go out there with a sense of wonder. If you're one of us, and if you want to explore more of this great planet, we're ready to take you there. It's time. Turkish Airlines. Widen your world.